Okay, so this is homework 5, problem 2. And so we're given that f of x and y is equal to 1 over a times x squared times y. For x is greater than 1, and the bounds of y go from 1 over x to x. So what does this look like graphically? It's in 3D, we can rationalize it. So when either x or y become very small, the value of f of x and y become incredibly big, because 1 over a small number is a very large number. And so near the edges of either the vertical plane of y equals 0 or x equals 0, near it the function approaches infinity. So it kind of looks like a quarter of a bowl. But since x squared, since it's 1 over x squared, then the x component, as x increases, decreases a lot faster than 1 over the y component, which is only just 1 over y. So the decrease in the x component goes down quicker than the decrease in the y component. So it'll be like a lopsided bowl. Alright, so to help us visualize the bounds of y, we can draw this graph here. So it's the graph of 1 over x, this is 1 over x, and this is the graph of x. And so y is for when is between 1 over x here and x, so it's just this shaded region. Okay, so now that we have these two graphically graphed out, we can move on to the next part of the problem, which is to find a such that this joint density function is valid. And so a joint density function is valid when the double integral of f of x and y is equal to 1. And so in this case, we have to choose the bounds, and in our case, it'd be easier to use dy dx than dx dy. And so we have 1 over a times x squared times y, which is the function of f of x and y, integrated over the bounds of y first, and the bounds of y are simply just 1 over x to x, and then integrated over the bounds of x, which is just from 1 to infinity, because it's just for x is greater than 1. And so we can take the component, since we're integrating in terms for y, the first part, we can take out 1 over ax squared, because that's a constant effectively when you're integrating with respect to y. And so we just get 1 over y. And so the integral of 1 over y is just ln of y. And so it's the ln of y from x to 1 over x. And so when you plug in x to 1 over x, you get ln of x minus ln of 1 over x. But because of the properties of logarithmic functions, this can be combined. Subtracting one log from another is effectively dividing the first log by the second, dividing the component of the first log by the component of the second log. And so it becomes, this whole thing can be combined as the log of x divided by 1 over x, which is the same thing as just log of x squared. And so you log of x squared divided by a times x squared. And so similarly with property of logarithmic functions, when you have ln of x squared, the 2 can simply just come out, so it becomes 2 ln x. So I take the 2 out in the front, and I take the a from the bottom out in the front of the next part, so it's 2 over a. The integral of ln x divided by x squared dx from 1 to infinity. And so this function, when you integrate it, we can do integration by parts, and we'll end up with negative ln x plus 1 divided by x from infinity to 1, from 1 to infinity. So this function at infinity, ln of x increases at a much slower rate than x does, and when the x approaches infinity, and therefore it becomes just small number over large number. So the x dominates when this function goes to infinity, and this value becomes 0. And then when we evaluate it for when x equals 1, ln of x is equal to 0, so it's just 1 divided by 1, so it's 1, so it's negative 1. But since we're minusing, so it's minus a negative 1, so it becomes a positive 1, so it's times 1. So we get 2 over a is equal to 1, because that's what a valid density function, the area of the valid joint density function actually equal. And so a just equals 2. And so our f of x to make a valid joint density function is just 1 over 2 x squared times y. Okay. So now we have to find and draw the marginal density functions of f of x and f of y. And so in order to find the marginal density function of f of x, we simply just integrate the function f(x) and y over the bounds of y. So we eliminate the component of y, so the function will be only in terms of x. And so taking this function, we can simply take out again like we've done before, 1 over 2x squared, because it's in terms of y, we get ln of y from x to 1 over x. We have done this step before, so it's ln of x minus ln of 1 over x. That becomes ln of x squared. The 2 comes out, so there's 2 ln x divided by 2x squared. The 2's cancel out, so we get ln of x over x squared for our f of x. And so that graph looks like this. This function does not exist for when x is less than 1, because ln log of a value less than 1 does not exist. And so this graph increases to a certain point until x squared dominates the function, and then this function goes to infinity. At infinity, it goes to 0. How do I know that? At infinity, x squared increases at a much higher rate than the log of the natural log of x. And so at infinity, it becomes effectively 1 divided by a very large number, which is equal to 0. So this slopes off to 0 when this function approaches infinity. Okay, so now to find fy, similarly to what we've done with fy, we have to integrate over the bounds of x to eliminate the component of x, so it's just in terms of y. But for f and y, it's a little bit trickier. So if you can see here, so for when y is from 0 to 1, the component here, because if you move this over, is this graph here of 1 over x. So we effectively have to eliminate 1 over x to infinity. So that's going to be the first bound. But this integral is only valid from the bound of 0 to 1. So that's our first integral. So it becomes f of x is equal to 1 over x to infinity of f of x and y dx. So the 1 over 2y can just come out, and then we get and we integrate 1 over x squared, and the integral 1 over x squared is just negative 1 over x, so it's that over the bounds of that 1 over y to infinity. And so at infinity, this becomes simply just 0, because 1 over infinity is just 0. And then at 1 over y substituted for x, it just becomes negative y. But since it's minusing a negative y, we get positive y. And so it becomes y divided by 2y, the y's cancel out, and it's just f of y is equal to 1/2 from y equal to 0 to 1. And now we have to consider from when y is from 1 to infinity. And when y is from 1 to infinity, we see here we have to take into account to eliminate this line here, which is just y is equal to x. So we have to go from y to infinity. And so f of y from y to infinity, so f of y, so the next component of f of y will just be from y to infinity of f of x and y dx. And so similarly, it's the same thing. We can take the 1 over 2y out as the integral of negative 1 over x from y to infinity. And when we plug in infinity, we get 0. And when we plug in y, we just get negative 1 over y. But since we're subtracting a negative 1 over y, we just get positive 1 over y. And so positive 1 over y times 1 divided by 2y gives us 1 divided by y squared for, of course, the balance only valid from y is greater than 1. And so our function here looks like from 0 to 1, our function is equal to 1/2. And then from 1 to infinity, our function is equal to 1/2 times 1 over y squared, which slopes down like this. All right. So for the final part of this problem, we have to verify that f of x and f of y are valid density functions, and they're valid if the integral over the bounds is equal to 1. So the bounds for f of x is just for x greater than 1, and so it's the integral of ln of x divided by x squared from 1 to infinity. And so ln of x divided x squared, we can calculate the integral by using chain rule, or integration by parts, sorry. So we end up with negative ln of x plus 1 divided by x from 1 to infinity. And so at infinity, this function is equal to 0 because x increases at a higher rate than ln of x does. And at 1, ln of x goes 0, so it just becomes 1 over 1. But it's negative, but we're subtracting a negative 1, it becomes 1. So therefore, the f of x is a valid density function. And so for f of y, we take two integrals over the two different bounds. So we take the integral of 1/2 from 0 to 1 because that is valid at 0 to 1. And that obviously equals 1/2. And for y greater than 1, we take the integral of 1 over 2y squared. So 1 over 2y squared from 1 to infinity, integral of that becomes negative 1 over 2y from 1 to infinity. And that's equal to simply just 0 minus a negative 1/2, which is equal to 1/2. So 1/2 plus 1/2 is equal to 1. And therefore f of y is also a valid density function.